Great. Thanks, Mike. Thanks. And it's great to see so many people here. Great to see so many young people here, especially. We're in a good place to use Axis. It's my great pleasure to be able to start this session off and give you an overview of Axis, and then sort of set things up for the science talks and a little bit of the instrumentation talks that will follow. So to set the scene, I think it's important to recognize that it was 23 years ago that Chandra launched. Just feels like yesterday, but it was quite some time ago, and Chandra brought a clarity to the X-ray universe. Literally, it let us image the X-ray universe in a way we never had before, and that changed astronomy. That changed all of astronomy. So this is just a sort of rogues gallery of some of the key results of Chandra. My own favorite picks. There's many here that have not made it, but in the left here we have the Chandra Deep Field, the deepest field, the Chandra Deep Field South, and some of those little points there are the faintest X-ray sources known. Some of those are the highest redshift AGN known. So this is key for probing AGN evolution. Over here are the Perseus cluster with Chandra. AGN feedback that is now all the rage across many wave bands. AGN feedback is an X-ray result. I will argue that with anybody. It's an X-ray result. The Perseus cluster is one of the key pieces of evidence that AGN feedback is happening today, here and now. Then we have the role of X-ray astronomy on stellar physics. So here's in the middle is stellar birth, the countless X-ray sources that are associated with the pillars of creation. We have stellar death, the supernovae remnants over here. And then even closer to home, we have the X-ray emission from planets. The planets are X-ray sources. That's through some very interesting physics, charge exchange emission, as the solar wind is bombarding the atmosphere of the planets. You get X-ray emission from a process called charge exchange. And that is a probe of both the planet and the solar wind. So this is just a give you the power of imaging X-ray astronomy. So Chandra gave us this view. Axis is the next step. Axis is an order of magnitude step beyond this in terms of our reach and collecting area. So we've been working on this concept for about 5 years now. This is our first science team meeting, which at University of Maryland, and Richard Mashotsky is a PI at this time. And Richard, it's a bleak angle; it's hard to tell where Richard is, but Richard's there somewhere. Real Richard is sitting on the third row back here. And we started putting this concept together for a large collecting area, high resolution X-ray observatory. Also one that is very respondent to transients, knowing that transient astronomy, time domain astronomy, multi-messenger astronomy is increasingly a key part of our fields now. What happened next is the decadal survey, of course, started machinating about the future of astronomy, and the decadal survey, in order to bring balance to the science program, given that the big flagship mission that they recommended, the Louvois X, is quite a long way in the future. It's 2045. They recommended that there be a new line of missions, these sort of probe missions, billion-dollar class missions. In fact, the decadal survey actually said $1.5 billion class missions that fill the gap, that start to bring balance to the program. And I've got the language here from the decadal survey that said in the coming decade, a far infrared mission or an X-ray mission designed to complement the ESA Athena mission, like powerful capabilities to address the key questions that the decadal survey had recommended. So that's where the Axis concept slots in. Okay, so what is Axis in a nutshell? Just to orient you for all the other presentations that will come. These are its key characteristics. It's a high resolution X-ray observatory. So what we mean by that is 1 arc-second point spread function on axis, 1.5 arc-seconds, so degrading. X-ray optics degrade as you go off axis, degrading to about 1.5 arc-seconds off axis. That is a very, I like to use language that Anne Hunschmeyer has used. It's a very graceful degradation as you go off axis, whereas because of the the design of the Chandra mirrors at that time, there's significantly worse degradation. So across our field of view, we have many more resolution elements than Chandra does. Plus, we have an order of magnitude more collecting area. So the numbers are here, significant field of view. And then the other thing I'd like to point out here is we are a fast slew rate. We can literally spin the observatory quite fast. And we will be very responsive to transients. Part of, to dig in a little bit to some of that, one big difference with Chandra is our orbit. We are in a low Earth orbit. We are spinning around just 650 kilometers up there. And what does that bring to you? That brings low particle background. The Earth's magnetic field is our shield. The Earth's magnetic field is deflecting away many of the charged particles from the solar wind, and is really giving us a very low background in our detector. Plus, it gives us very fast communications to the satellite. So if we need to get an alert to the satellite saying, point over there, we can get that up fast. And right now, by fast, we mean 2 hours from alert to point to being on target. So that's what low Earth orbit does. Okay, so to sort of map out the observing time budget for this facility, even though the science team that has been put together to be responsive to the NASA call, that we have to put forward a science program that we will be judged on and the proposal will be reviewed on, that can only be 30% of the observing time. 70% of the observing time from AXIS will go to the community. And what that means in terms of actual time for a 5-year mission, and assuming a 70% observing efficiency, so 30% of the time, you're either in the process of slewing or you're passing through a high radiation zone, the so-called South Atlantic anomaly, or something else is going on, you're calibrating or something like that. But assuming a 70% observing efficiency, then the numbers pan out like this. It will be almost 17 megaseconds of observing time available to the general observer community for observer targets. Maybe 30, but let's just say the breakdown between the guest observer TOOs and the guest observer targets is completely arbitrary. It's up to the observers and proposal pressure really where that sits. But in what we envisage, there'll be 13 megaseconds available for TOO responses, and then the science team program that we are putting together, the science team, fits into 34 megaseconds. So there's a very large part of this which is community driven. In fact, part of our proposal is to try to forecast what you will be wanting to propose for in the 2030s for this mission. So part of our proposal is actually to try to guess what the community will be proposing. We have 5 science working groups, and in fact, you'll be hearing from each of those in this session. And these are the groups listed off, and I'm listing here the leads and co-leads of those groups. And at this point, I know there's many members of these groups sitting in this room. I want to thank you for what is a lot of work that has been put into what you've been doing. As we've been putting together the science case for this observatory that we will be judged on when we go into these formal proposal processes in NASA. So I won't read this off, but this covers a significant part of the science of the decadal survey. It covers the science decadal survey that we believe that AXIS is most responsive to. So there's something which many of us live and die by, and some people it sounds like bizarre terminology, the science traceability matrix. This is how you turn science into bureaucratic speak, where you have your top level questions, you turn them into measurements you want to make, you turn those into your mission requirements, and those become engineering requirements. So this gives you a flavor of the kind of science the kind of questions that we'll be able to ask with AXIS. And importantly, also gives you a flavor of the reach that AXIS will have. So the decadal survey broke the vast range of interesting astronomy and astrophysics and cosmology questions into 3 broad themes: cosmic ecosystems, meaning galaxy evolution, stellar evolution, AGN evolution, new messengers and new physics, gravitational waves, transient astronomy, dark matter, dark energy, and the worlds and suns in context, exoplanets, the connection of exoplanets to their stars. Axis will have reach across that whole set of problems. And listed here are actually verbatim some of the questions that the decadal survey recognized as the key questions, and how we'll be able to address them. So in fact, a lot of talks you'll be hearing next are drilling into some of these topics. So I won't just read these out, but you can see them. So just to sort of whet your appetite, let me just dive into a couple of these. This is what an axis deep field would look like. So hopefully the room is dark enough that this can look like a very boring figure if the room is too light. You just see a big black square. But you should be seeing a big black square with lots of point sources in it. And those point sources are, thanks, Andy. Oh, no, okay. Light switch doesn't work. So there's about, there's almost, not quite, almost about 10,000 point sources, about 8,000 point sources in that deep field. This is 5 megaseconds. Extra-astronomers thinking, there you go. Okay. It's full of stars, yeah. So now half of those sources, in this simulation, half of those sources are AGN, and half of those sources are the X-ray emission from galaxies. Most of those being quite high redshift, and some of those being very high redshift. And as we'll hear from the AGN group, from Adi, that one of the key science questions is being able to probe AGN, low luminosity AGN, but high enough redshift that we start to become sensitive to what the seed black holes were. Did supermassive black holes start their life as the remnants of POP3 stars, or did they start their life as so-called direct collapse, 10 to the 5 solar mass black holes? That's one of the key questions here. Another question that again you'll hear from Adi about, and sorry for the AGN slant in this talk, but I'm an AGN guy, so is the role of dual AGN black hole mergers. So this is actually real data. This is Chandra data on the system NGC 6240. This is a dual AGN. It's a merging galaxy. Both cores of the galaxy are AGN, and we can see that with Chandra. You can see the 2 point sources in there with Chandra. So with Chandra, we can see that, but with axis surveys, we'll be able to have a large enough survey at deep enough redshift. We'll uncover many of these sources, and Adi will tell you how many we'll uncover, and what we'll learn from that in terms of the role of AGN, of black hole mergers in the universe, and how they build up black holes. To sort of skip to the other end of the science problem, X-rays actually have interesting things to say about exoplanets, which is initially maybe a bit surprising. But just to sort of show you one really neat result from Chandra, this is the transit of an exoplanet across its star in the X-ray band. And you can see how when the exoplanet transits the star, there's actually a dip in the X-ray emission. So the X-ray emission is going from the star. It's the stellar activity, or the flares and activity from the star. And as the exoplanet travels in front of it, it blocks that X-ray emission. The interesting thing is that the transit in the X-ray emission is deeper than the transit in the optical emission. So what does that mean? Well, this is what we think it means, that literally the activity of the star, the X-ray activity of the star, is evaporating the exoplanet. The atmosphere is being evaporated off. And with X-rays, we can see that it is X-ray absorption from that plume. And that's what we're seeing here. So that's just an indication of just how important stellar activity can be on exoplanets. But more generally, exoplanet science is here already, and will only become more important. With JUST, we're already starting to look at the chemistry of exoplanet atmospheres, and again with future data that will only become more important. So the chemistry of an exoplanet atmosphere is going to be tied to the X-ray activity of its host star. Understanding that is key, and with AXIS we'll be able to do a population level survey of stars to understand the activity. So this is I'm gonna not go on any longer and let the rest of the session continue. So hopefully give up some of my time for discussion questions later. This is the rest of the session. Hopefully this is the latest up-to-date schedule. So again, the first 5 of these talks are from our science working groups. And then we'll hear a little bit about how we're actually going to do this. One of there's 2 key pieces to this observatory. One is the mirror, and one is the camera. So how we're going to build the mirror, how we're going to build the camera, and that's what we'll get to later. Will is it's a video. Yeah, it's a movie talk from Will, because Will is literally busy building mirrors. And that's what we want him to be doing. And then Eric is here telling us about the camera. So let me hand over to Addy.
All right. Hi, everyone. So my name is Adee Foord. I am a Porat postdoctoral fellow at Stanford. And I'm co-lead for the Supermassive Black Hole Science Working Group for AXIS. And Nico Capilouti, who's perhaps somewhere in the audience, there he is, he's the lead. All right, so today I'm going to be focusing on AGN survey science with AXIS and how it's really going to push our understanding of the origins of supermassive black holes and their growth over cosmic time. So Chris already showed this figure, and I'm going to delve in just slightly more detail because I think it's really great, but we probably don't have to turn the lights off again. I hope everyone got the view they wanted. But in general, in the post-Chandra era, it will be very important to have a high-resolution X-ray imager. And some of the key takeaway points from this figure is that AXIS will, 1, have a much larger field of view. So this is the 24 arc-minute by 24 arc-minute field of view, and the ASIS-I footprint is overplotted in white. It will have a much more stable PSF. So we're looking at zoom-ins of different panels, one that's on axis in blue, one that's 4 arc-minutes off axis in yellow, and one that's 7 arc-minutes off axis in red. And if you look at the panel on the right-hand side, you can see as you move off axis, the PSF of axis remains quite stable and symmetrical, whereas Chandra's PSF begins to degrade quite quickly beyond about 3 arc-minutes or so. And then lastly, the effective area of axis is much better than Chandra's. So it's about 10 times better at 1 keV. And so in the center of this simulation, we put a Z of 3 cluster. And you can see in that blue zoomed in panel that axis is actually detecting some emission associated with that cluster, whereas Chandra is not sensitive to it. So all of these things combined is really going to revolutionize our understanding of supermassive black holes. So in general, with the current X-ray surveys, there are still a lot of high Z quasars that are missing. And the one way to fix this is to have surveys with more depth and more survey area. So this is showing the survey flux limit versus the survey area for a handful of X-ray surveys. So on there, you have the Chandra CDFS survey, as well as the Chandra Cosmos Legacy field. And we're overplotting AXIS's surveys, so a deep survey, a medium survey, and a wide survey. And so the deep survey with AXIS, we can reach flux limits on the order of 10 to the negative 18 ergs per second per centimeter squared. And with the wide surveys, we're going to start expanding the known population of Z greater than 6 quasars. So with this wide, intermediate, and deep field survey, AXIS is going to be detecting over 200,000 AGN, and over 90% of these objects will be detected for the first time in X-rays. So this figure is showing the AXIS detections in black from the combination of these 3 surveys, their X-ray luminosity versus their redshift. And then overplotted are 2 different predictions that seeding models have for the number of AGN expected given their luminosity and their redshift. So you can see that a heavy seeding scenario has a different projection than a light seeding scenario, for example. And so in general, expanding the population of higher Z quasars and comparing it to model predictions will allow us to better understand which scenarios may dominate and what may be happening at even higher redshifts. And another way to look at this is the luminosity function of supermassive black holes and how this varies as redshift. So these are results from semi-analytical models that tracked the evolution of supermassive black holes, prescribing a handful of accretion modes and looking at two different seeding scenarios, so a heavy seed scenario and a light seed scenario. And I know it's a lot of lines, but the main takeaway point, if you look at the Z equals 10 panel, for example, the heavy seeding model predicts more luminous supermassive black holes, and the light seeding scenario predicts more dim supermassive black holes, for example. And so in general, populating the known number of AGN at redshifts of 6, 7, or 8 will allow for an unprecedented fine-tuning of all of these various models with respect to the data, and will allow us to better constrain these parameters that describe all of these seeding scenarios when comparing them with the data. Oh, and I should add that in the dashed line is the sensitivity that we can get with a very deep axis stare. Okay, so I'm moving fast because I don't have a lot of time, but I'm now going to be focusing on how do supermassive black holes grow. So the axis-wide, intermediate, and deep fields is going to yield the most tightly constrained measurement of the evolution of dual AGN across cosmic time. Dual AGN are pairs of AGN that are in the process of merging. So you have two supermassive black holes, they're actively accreting, and they're merging. These are results from theoretical models that looked at the growth of supermassive black holes as a function of redshift and mass. And these black holes were either growing through the accretion of cold gas or through mergers. And so in the farthest galaxies away at higher redshifts, low mass black holes were seen to be growing mostly through mergers, whereas high mass black holes were seen to be growing mostly through accretion. And in the more nearby universe, this is reversed. So low mass black holes are mostly growing through accretion and high mass black holes are mostly growing through mergers. So quantifying the rate of dual AGN as a function of redshift traces the underlying merger rate of supermassive black holes as a function of redshift. And seeing how this changes over cosmic time will give us better insight into what the universe's environment looked like at those different periods. So AXIS is going to discover over an order of magnitude more AGN pairs than currently capable with Chandra, which is extremely exciting. This figure is showing the dual AGN fraction, or the fraction of AGN that are actually two things, as a function of redshift. And I'm showing predictions from hydrodynamical simulations in dark green, as well as a nearby constraint that was placed by Mike Koss. There's a discrepancy between these two measurements, and there's many reasons why you might expect that. But what we've also done is we've taken those hydro simulations and we've scaled them so they're anchored by that nearby constraint, just to see what that evolution might look like if it actually continues from that measurement. So with Chandra, you can try to take all of the data in the various deep and wide fields and try to measure how many of those AGN are actually dual. And the sample is very much constrained by the off-axis angle of your AGN. So this is just showing a handful of what we believe are single AGN that have off-axis angles greater than 3 arc minutes. And it's you lose a lot of sensitivity in parameter space when trying to determine if it's 1 or 2 AGN because the PSF is so extended. So the sample size is small. And so when you're trying to predict which fraction you might measure, your error bars are quite large. AXIS is going to completely revolutionize this field with its extremely large number of new AGN that we can analyze for the presence of any merging pairs. So at each redshift bin, you can see that the error bars are very much smaller than what you might get with the Chandra sample. And we can expect to find hundreds to thousands of new dual AGN with AXIS. So this will allow for population studies, as well as really accurately constraining that dual AGN fraction across cosmic time. And then I'll just lastly say before I get off the stage that there's so much more AGN science that AXIS could do. I'm really only focusing on 2 main pillars. And in general, AXIS is just going to change the field of how we view supermassive black holes. So thank you.
you want to take a time for a question or two?
Oh,
Yeah, but
sure.
are there any questions on AGN with access? If there's a microphone at the front, or we have one here. Or we can just do the questions at the end.
I'm itching to make a comment.
Okay, you can make a comment. Good comments. Too.
Yeah. It's all very important, and I sort of agree with everything you said and more. But I've got to say, the pedantic pair of AGN, a kiloparsec apart, is not a merging pair of AGN. We think that they'll merge. There's theories that say dynamical friction will merge, but we don't know. They themselves are not a merging pair. I think we have to push down to finding pairs. And I know you're looking at hundreds of parsec pairs, and that's good. I think we have to push down to tens of parsecs or lower to say that we really have merging pairs. And that's important to do.
Yeah, so I completely agree. And one thing that I will say, a different perspective, looking at the sample that Axis is going to bring, is that you're going to be able to find many more pairs at various separations. And what you can start to do is try to link that with the galaxy properties as well. To try to better constrain, are there certain environments like major mergers, for example, gas-rich mergers, where you might actually expect these things to be moving in close to each other? Is there a certain region of parameter space where things might look stalled? So in general, I think the environmental studies that you can do with these thousands of new dual agent candidates that will come in will give some insight on the specific environments that allow mergers to happen.
Are there any other questions or comments? Go ahead.
You know, one thing that I always wonder about the dual AGNs that are particularly close, you always have run the risk of there being some emission difference with AGN. And one thing that you get with more photons is the check for variability. So you get an extra check on top of just being detected these two things spatially.
Yeah, so I think that that's a really good point. And then even just to add on that, these survey fields are likely going to be overlapping with like JWST survey fields as well. And so that is also going to give you a lot more information on whether or not you expect a merger, for example. Yeah.
Okay, great. Let's maybe move on to with that. Go ahead.
So one of the key questions that was posed by the decadal survey is how does stellar activity affect evolution and habitability of extrasolar planets? And ACCESS is extremely well positioned to answer this question. This chart shows the ingredients that go into making a habitable planet. And one full quarter of it describes the properties of the host star of that planet. And X-ray luminosity corresponds strongly with many of these properties. For example, variability and magnetic fields is something that is being traced by the X-ray activity. And the reason why we want to know the stellar activity is because it has an influence on stellar atmosphere, on the planetary atmospheres, in that a very active star would be able to strip the atmosphere of a planet, as was demonstrated earlier. Here, on Earth, we are orbiting around G-type star, but the most common types of stars out there are M dwarfs. They are 10 times as abundant as G-type stars. The same is with M dwarfs, because they are less luminous, the habitable zone is significantly closer in to a star for these planets. So they receive 400 times the irradiance, X-ray irradiance that we get here on Earth. So that could be a crucial element for habitability of these planets. And to make the matters worse, here this shows the evolution of spots on the surface of the star as a function of age. stars start out their lives fairly active, but M dwarfs remain pretty active throughout their lives in comparison to the G-type stars. So that effect of high activity is magnified for low mass stars. But overall, if we were to look at the X-ray emission specifically, it starts out very high in stellar lifetimes. It plateaus for a while because magnetic fields are saturated, but then it eventually precipitously declines over time as the stars lose their activity. The thing is about these diagrams, so they're fairly sparsely populated. There's only a handful of points because only a handful of clusters have been observed in the past with Chandra. On the younger end, we're doing a bit better, but over the full range of ages, there's only a handful of clusters. And there's significant scatter that we still don't really understand the origin of. So this is something that we really need to do much better. Even in the data that we currently have right now, we can do much better. For example, this is the Orion Nebula. Chandra had observed it with a very deep exposure called Chandra Orion Ultra Deep Field. It stared at Orion Nebula for a period of around 14 days continuously. It is an extremely deep survey that managed to capture X-ray emission of almost every single star in this cluster. And it looks great. This still remains to be a golden standard of our understanding of stellar activity in young stars, even 2 decades later. But as you can see, Chandra's resolution significantly decreases off axis. You can see that close to the center of the cluster, you have very crisp point sources. As you get further and further out, you can see the PSF smearing out. This is a very dense cluster, so having good resolution is important to be able to resolve stars apart from each other. This is also fairly nearby clusters. There are many clusters that are significantly further out that have slightly different velocities that we need to take into account. Their resolution becomes even more important because further away, everything is going to become significantly more compact. But this is also only just one small region in the sky. Just to give you some context, this is the entire Orion complex. This is the entire constellation, spans 20 degrees in the plane of sky. There are many star-forming regions in here. Some of them are pretty dense. Some of them are extremely diffuse. We do know that environment in which stars form does influence some of the stellar evolution. For example, if a star is found near a very massive star, then it would have a different effect on its disk, for example. Orion Nebula is found right over here. It's just the densest part of Orion. It is extremely massive cluster, but it is also relatively compact, especially in comparison to this entire region. The Koop field is just a tiny portion of the Orion Nebula. So it's just the densest part of the densest clusters. It's not really representative of the entirety of star formation that we know of. So by having greater sensitivity, even so ACCESS should have approximately the same field of view as Chandra, by having greater sensitivity, we would be able to map many more regions in the sky, many more clusters found at many different environments faster to achieve similar sensitivity. So just to summarize, ACCESS would be extremely useful for characterizing stellar evolution, from understanding how activity of the stars changes throughout as they age, how stars flare, what effect they have on exoplanets, and what is the origin of the scatter in the X-ray luminosity as the stars age. Thank you.
So we have time for a couple of questions. So I'll actually ask a question. So with the landscape of JWST and really being able to see through a lot of the dust, how will that be important for kind of finding new systems to study in the X-rays and new possible?
So with James Webb is good for very pointed observations. So it's not that useful for the discovering these large structures, but it's good for understanding them in greater details. There are a number of other surveys that cover the entire sky. For example, Gaia was revolutionary in finding all these new populations, understanding what they are, how they're positioned in the sky. For example, we didn't know half of the Orion before Gaia. TESS is very useful because it shows us optical variability, some of our current understanding of the stellar variability and spots comes from TESS. Many other large surveys that cover the entire sky. So I think those would have the greater synergy with something like this.
Okay, great. Any questions? Okay, maybe let's move on.
Here's my wallet.
Yeah, it's up, down.
Okay, great. Okay, hello everyone. Thank you for being here at this late hour. I guess that implies that you're very enthusiastic about X-ray astronomy. As an X-ray astronomer myself, I have to start by saying I can't really imagine the future of X-ray astronomy without continuing to have high resolution imaging, especially for someone who works on these objects, compact objects and supernova remnants, often in very crowded places in our galaxy. So I'm Samar Safi-Harb from Canada, and I'm presenting this on behalf of the Compact Objects Supernova Remnants Science Working Group, which is shown here. So you can see a panoramic view with high resolution of members of the group, many of which are young, early career researchers, and I think a few of them are here in the audience. And I'm leading this together with Kevin Burns from MIT, shown on this slide. So I'm going to focus on our galaxy, and for the extragalactic people in the audience, I would say that our galaxy really presents a nearby lab for a whole range of high-energy astrophysical phenomena associated with the death of stars through massive explosions and their impact on the environment, which ultimately affect the dynamics and evolution of galaxies. So I'm going to have a number of science cases. Hopefully I can go through all of them. If I run out of time, please, Mike, feel free to stand up and stop me. So I'm going to start with the population studies, starting with the galactic plane survey. And as Chandra showed us, the high angular resolution was important to discover many classes of compact objects. But what will AXIS do is detect, go deeper and take us down to 1 or 2 orders of magnitude deeper in terms of the X-ray luminosity function. So what you're seeing on the right is the X-ray luminosity function obtained with Chandra for some 10,000 sources, reaching luminosities of the order of 10 to the 32 works per second. So AXIS will detect X-ray sources down to 10 to the 30, 10 to the 31 works per second at an assumed distance of 8 kiloparsecs. AXIS will provide sub-arc-second positions, which is needed for multi-wavelength counterpart matching, especially in dense areas, as illustrated in this just one sample field from the plane of the galaxy. With AXIS Galactic Plane Survey, we will detect some 3 million sources per square degree, which will imply we need to start using new techniques for classification of unidentified sources that has been already applied to some 66,000 sources from the Chandra X-ray catalog, as illustrated in this very recent study. And this figure just shows a comparison between Eros-Theta 1 kilosecond versus a simulated axis of a crowded field in the plane. These are representative survey depth for Eros-Theta versus axis, assuming a 1 arc second point spread function. Zooming in on the heart of our Milky Way galaxy, there's this fascinating, stunning image of the region around Sagittarius A star. This is a colorful image which combines Chandra with the recent Meerkat radio observation. And if you were to zoom on the box right around Sagittarius A star right here, you will see that it's really very crowded even to that level. So this is a 12 by 12 arc-minute field of view, roughly half the field of view of axis. You'll see there's lots of types of sources. Pick your favorite. There's supernova remnants, runaway neutron stars, non-thermal filaments, multiple point source populations, molecular clouds, and a magnetar. The magnetar in particular is very close to Sagittarius A star, just 2.4 arc seconds away. And so the imaging resolution is absolutely needed, and an axis observation of the galactic center will continue on the Chandra legacy for galactic center monitoring, which will enable a whole range of studies, including monitoring SGR A star, which will provide synergies with the Event Horizon Telescope and gravity, for example. There's also a bunch of transient, extremely faint sources within the central parsec of Sagittarius A star, and AXIS will enable the detection of these faint point source populations. Another crowded field is globular clusters. And by studying these, we can address these two questions listed at the top, which talk directly to Astro 2020 pillars. What you're looking at here is a deep, more than half megasecond observation with Chandra shown side by side with Hubble, just to illustrate the density of sources in those fields. And of course, the sensitivity of AXIS, an order of magnitude improvement over Chandra, as well as the excellent PSF over the large field of view, will make the observations of globular clusters much more efficient. So the equivalent to this very deep 47 TAC observation can be done only with 50 kiloseconds with AXIS. And that means we can go much deeper into the faint end of the X-ray luminosity function of globular cluster, going down to about 10 to the 29 ergs per second. Moving on to the neutron stars zoo, which is shown here on the right-hand side of the PP dot diagram. I talked about this in the next slide in my talk yesterday in the special head session on galactic autopsies. So I'll just very quickly say that we have a wide range of different zoo of neutron stars, from rotation power pulsars to magnetars to anti-magnetars. And we're only seeing the tip of the iceberg. Swift and Chandra in other X-ray observations have enabled the discovery of magnetar-like behaviors from anti-magnetars connecting the zoo, and AXIS will help discover magnetar-like outbursts from many members of this, particularly the faint population. And that will help bridge galactic sources to extragalactic sources, particularly because of the recent discovery of fast radio bursts from a galactic magnetar. So by studying the diversity of neutron stars in our galaxy, we can really connect the dots to the diversity of extragalactic sources. There's also a zoo of pulsar with nebulae. I talked about that yesterday as well. The high power no puff, the schizophrenic, the cosmic ray factories. The point is that without Chandra, this field would not have blossomed. Thanks to Chandra, we discovered many important results from these observations. On the right, you see AXIS simulations on just a few pulsar nebulae. The termination shocks, which are the sites where particles get accelerated to ultra-high energies, are just sub-arc seconds or arc seconds away from the pulsar. These help us probe directly the magnetic field, which is now being imaged also with X-ray polarization. For the supersonically moving pulsars, they create those narrow and faint trails and misaligned outflows, as shown in one of these pulsar wind nebulae. These have been used to study the cosmic rays, leptonic content, and diffusion in the ISM. There is significant synergy between these studies and gamma ray observations in particular, where there is a new field born in gamma ray astronomy, particularly in TeV astronomy, by discovering pulsar halos and galactic penetrons. On supernova remnants, studying the effect of supernova shocks on the environment, Chandra has led to the discovery of non-thermal X-ray emission from bright supernova remnant shells, as well as variability from knots, like shown here in this famous non-thermally emitting supernova remnant. Obviously, the imaging resolution is very important. By having excellent PSF over a large field of view, one can look for these features also throughout the remnant shell. This is important because the thinness of the filaments, as well as the variability, is evidence for magnetic field amplification, which is key for nonlinear diffusive shock acceleration. So I see Mike did stand up. This slide talks about the link to fundamental physics, basically measuring cooling of neutron star temperatures, which can be directly linked to the presence of superfluids inside the core of neutron stars, and measurement of the neutron star kicks, which is important for studying the mechanism for supernova explosions, as well as putting constraints on the binaries that stay bound and remain and become gravitational sources. The last slide is on the synergy with LISA and AXIS, enabling us to discover a number of binaries with white dwarfs through X-ray periodicities. The large effective area will enable the discovery of many photons, but also these are in crowded fields, so the imaging resolution is also needed. So there's lots more, but I'll stop here and thank you for your attention. And I'm sorry about going over time.
No, that's okay.
So you described something that was called an anti-magnetar. What is that? It obviously cannot be a magnetar root of anti-magnetar.
Yeah, thank you very much for asking that interesting question. So one of the problems is the way we name things, obviously, but so magnetars are typically believed to be highly magnetized neutron stars. So if you look at this diagram, they have magnetic fields above this line, which is 4 × 10⁻13 Gauss. So they are somewhere in here. The guys that are called anti-magnetars are these central compact objects. In fact, these objects have been discovered with Chandra, and they are typified by the Cassiopeia A neutron star. These objects are called anti-magnetars because 3 of these three objects within the sample have measured periods and period derivatives that imply a magnetic field of the order of 10 to the 10 to 10 to the 11 Gauss. So very, very low in comparison to magnetars. So they have been dubbed the term anti-magnetars. So that, with that said, outbursts have been observed from one of these objects. So what do you call magnetar? Outbursting sources or high magnetic field pulsars? I guess that's a question that's should be debated, but excellent question.
Okay, great. So maybe let's switch to transients.
All right, thanks.
Hey, hello everyone. My name is Yuhan Yao. I'm a graduate student at Caltech. I will talk about the important role that AXIS will play in areas of time domain astronomy. I want to start with an overview of what time domain and multi-messenger missions we will have 10 years from now. This is by no means a complete list, but it should give us an idea of what's being prepared from X-ray to radio and from high frequency to low frequency gravitational waves. For GW detectors, LIGO Voyager will be able to find binary neutron star mergers out to redshift 0.5. In the X-ray, their jetted outflow emits afterglow emission, which tells the observing viewing angle and the jet structure. Going to long period systems, continued operation by pulsar timing arrays will find supermassive black hole mergers. And more excitingly, the space interferometer LISA will find intermediate mass black holes out to redshift 10. And for those events that are occurring in gas-rich environment, we expect X-ray emission from the accretion processes. Now, one thing I want to highlight is that the current generation of X-ray facilities are not sufficiently sensitive to events out to the gravitational wave horizon distances. And that's why access will be so important to localize and characterize the high energy electromagnetic counterparts for those gravitational wave sources. And similarly, next generation EM surveys will also probe the dynamic universe out to a really large volume. For example, the Ultraviolet Explorer and the Rubin Observatory LSST will be more than an order of magnitude deeper than the current Zwicky transient facility and the ultrasat surveys. This means that they will really probe the bottom end of the luminosity functions of various transient populations. And in the X-ray band, we really want to have a follow-up facility to have a sensitivity to at least match those provided by the discovery engines, such that we can really seize the opportunities to constrain the rates to characterize the long-term evolution of the multi-wavelength emission and to find peculiar events. So in the rest of this talk, I will talk about two science cases that will be benefit from the excellent sensitivity and effective area that access provides. The first type of transients are luminous fast blue optical transients, or LF bots. Here, fast means that they brighten to peak in just a few days because the optical emission is powered by the interaction of the outgoing material with the gas in the ambient medium. Blue means they're very bright in the ultraviolet light, which tells that the temperature is very hot. LF bots are more energetic than ordinary F bots, and they are accompanied by very luminous radio and X-ray emission. From the X-ray observations, people inferred that there was not only a single release of energy that sort of happened and it was over, but instead there must be continued generation of energy from a very small emitting region, which we call an engine. And one of the promising ways to form an engine is that in the depth of a massive star, the stellar core collapses into a compact object, such as a black hole or a neutron star. In a normal supernova, the compact object just stays there. But in an LF bot, the engine can be very active. One of the major open questions in this emerging population of massive star explosions is the nature of this central engine. And for this problem, the shape of this X-ray light curve provides an essential diagnostics because the X-ray band probes materials that's closest to the central powering source. For example, in this LF bot AT 2020 MRF, late time Chandra observations have shown that this source exhibits daytime scale variability even 1 year after the explosion, which can only be explained by either a highly spinning magnetar or a very actively occurring black hole. I think the most challenging problem in studying LF bots is that their volumetric rate is very low. So to construct a sample of events with good X-ray coverage, we want to make sure that every year, at least one object can be followed up in the X-ray down to a meaningful luminosity limit around 10 to the 40 ergs per second. And this requires an X-ray sensitivity at few times 10 to the minus 16 erg per centimeter square per second, which speaks for the requirement of the really sensitive instrument. The second type of transients that I want to highlight is tidal disruption events. When a star comes too close to a massive black hole in the center of a galaxy, it will be torn apart by the tidal forces. Roughly half of the stellar material remains bound to the black hole. They fall back to form an accretion disk. In the following months to years after this disruption, the expected stellar debris mass fallback rate exceeds the Eddington limit. So by studying the X-ray emission from this newly formed accretion disk, we can start to understand super Eddington accretion. For example, fast outflows are often seen in numerical simulations, but observationally, they are poorly characterized. In the X-ray band, such ultra-fast outflows manifest themselves as blue shifted absorption lines on top of the continuum emission, because as a result of the high radiation pressure, some of the disk materials are moving very rapidly towards us. Among the roughly 100 TDEs known so far, such features have only been robustly detected in one source, Assassin 14Li, shown here on the right. You can see a very broad absorption line here in the early time data, which is consistent with oxygen blue shifted by 0.2 C. So in the future, AXIS will be able to study more nearby TDEs and study the evolution of the energetics and velocities of the ultrafast outflow to understand super Eddington accretion. And in addition, detailed X-ray observations on nearby TDEs can also help us to constrain the spin of the otherwise quiescent black hole. As you may know, the traditional method to constrain the black hole spin is to model the reflection spectrum, where a fraction of the continuum emission from the corona is reflected off the accretion disk. And by modeling this reflection component, one can simultaneously constrain spin, the inclination, the ionization state, and so on. Although the majority of TDEs are known to be soft X-ray emitters, surprisingly, in the recent TDE AT 2021 EHB, roughly a few weeks after the optical discovery, we start to witness the real-time formation of the corona above the accretion disk. Here shows the new star and nicer observation of this TDE, where you can see a very prominent non-thermal emission and an extremely broad line consistent with the fluorescence of iron. So in the future, we want to find more of TDEs that develop corona in their late time evolution and to use AXIS maybe in combination with the hard X-ray instrument to use reflection spectroscopy to constrain their black hole spin. So with that, I'm leaving my summaries here and I'm happy to take any questions. Thank you.
So do we have any questions?
Yeah, 13% is like 10 kiloseconds a day. I wonder if the team has done work yet on what the cadence of the time targeted opportunities might be. Might you have one a day or two a day, or maybe 2 week long TOOs and maybe only 10 a year? And that's probably you'll do all those possibilities, but so the question is, have you worked at that level of detail yet of what the actual timeline of TOOs might be?
I think one thing we know for sure is that we will have very fast response for the TOOs. The fraction of time devoted to TOO triggers is currently not as high as, say, Swift or NICER. So we can use Swift or NICER to track the long-term light curve evolution and to use AXIS to conduct the really detailed spectroscopy or the really late time observation. At the late time, say a few years after the explosion, the evolution will be a fraction of the age of the transient. So say 3 years from the explosion, the variability timescales might be 3 weeks, not as high as early time. So we 30 kiloseconds, I think we can still do lots of follow-up. Or if
I'll take that as a no, which is okay. I mean,
Go ahead.
We're still in the early stages of detail study, but we're carrying forward a number of approximately 10% of observing time in weeks for those responsibilities in terms of planning. The implications of engineering, we think that's something that was. This is an incredibly active field, and we'll assess when to continue to assess that, but that could be. I imagine up to 1 a day. I know that with fast response, that's okay. It depends what you do with it, then trigger and then have a monitoring program that follows up.
Great, so maybe let's keep moving on. So our next speaker will be Lanz, City College of New Jersey.
Now, just the College of New Jersey.
The colleges.
So yes, I'm Lanz, and I'm going to tell you a bit about our goals on the side of galaxy evolution and feedback. The lead of that science working group is Helen Russell, and the co-lead is Laura Lopez. And I'm actually going to start with our summary figure, which kind of highlights the diversity of questions that we want to ask in this area, and the gain that we get over AXIS. Chandra has done phenomenal things for our understanding of the most massive and brightest of these sources in the universe. But with AXIS's much greater sensitivity, we can start to try to connect that to the cosmic web and really get an understanding of both the interplay of gravity and feedback in the local universe, but also how that evolves over cosmic time. And so we have a science pillar that is focused on the high redshift, and then we have one on stellar feedback and one on AGN feedback. So I'm going to start on the high redshift side and give you a sense of a couple of the things that we've been looking into. And hopefully after our first plenary on Monday that Jane Rigby gave so wonderfully, I don't have to convince you of the power and magnitude that lensing gives us. And there's already hints in deep Chandra stacks of Einstein rings in X-ray observations, but with AXIS, and particularly with its spatial resolution, we can start to find these, and with these kinds of lensed quasars, try to probe the connection between the tiny scale ultra-fast outflows in these quasars and the larger outflows on galactic scales in these systems. We've also done wonderful work, as Chris showed us, with Perseus in the local universe, but we also want to push that question out to higher redshift. And here you have some simulations done of what AXIS could do as you go from a redshift of around 0.5 of a cluster and push it out to a redshift of 1, 1.5, and 2. And by the time you get out to 2, Chandra can't do anything for you, but AXIS has a chance to do it and trace that back to the present day. And so within the high redshift area, we have 3 main questions that we want to ask. When did the first galaxy groups and clusters form? When and how did AGN feedback start to shape their evolution? And when and how did the enrichment of the hot and diffuse universe really start to happen through the presence of heavy elements? But in addition to wanting to probe the high redshift part of the universe, we also want to look at the nearby universe to really resolve some of the key physics and look at the relative effects of both stellar feedback and AGN feedback. And I'm going to spend a little bit of time on a couple different ways that we can look at nearby galaxies. One of the things that we still really want to look into is the effects of jets and winds on host galaxies. And having a really good spatial resolution, really good PSF, is important for being able to resolve the soft X-ray gas and look at this aspect in comparison to the radio images that we'll be able to get at that time, as well as optical and infrared, and look at how the hot gas plays a role compared to the other phases of gas in these systems. To give you a sense of the power of AXIS, I've also shown here on the bottom, I have a set of data collected over 2 different cycles with Chandra. And this upper line that I'm sure at the back is you're barely able to see was cycle 11. And then down here you have cycle 18. And that's because over time, the soft response of Chandra has been degraded. And since cycle 18, it's not gotten much better. So I took the same system. So this is a nearby lenticular with quite a bit of hot gas. And I did some simulations of what I could do with Axis. In 6 times less exposure time, so only 25 kiloseconds as opposed to 150 kiloseconds, I can get at least twice as many photons. In some cases, depending on the model, as many as 4 times as many. So that could allow me to do a finer spatial binning, and so look at the evolution of, say, the temperature as you go away from the AGN. Or it could be a way of going, well, okay, I've looked at this one galaxy, and now I can do 6 galaxies instead of 1, so I can start to look at larger populations of galaxies. Or you could look at galaxies that are significantly further away, because with the same sort of exposure time, you're getting to dimmer, fainter things, which can correspond to more distant things. So the greater sensitivity of Axis lets us probe larger volumes, larger samples of galaxies, more distant galaxies, and with that, look at both a wider variety of processes, but also more distant cosmic evolution periods. While we don't have a specific science question on groups, we have had some wonderful discussions about the fact that groups are not just small clusters, and that they provide a really interesting way of looking at the evolution and the change of physics and feedback physics as you change the mass of the system that you're looking at. This is a Chandra image of NGC 5813, unless I've mixed up some of those numbers, that Scott Randall put together. And this was a legacy class image that, that Chandra put together. But with the greater sensitivity of Axis, this could be, if not completely routine, then much more commonplace to get this quality of data on these kinds of systems. We also have 3 questions for nearby AGN feedback. We want to understand how powerful radio jets provide heating in galaxies and cluster environments, particularly in a self-regulated way. We want to understand the impact of AGN winds and whether they can drive galactic scale outflows. And we also want to probe feedback processes down to Milky Way mass galaxies. Is the physics just cluster processes scaled down, or do the physics change at some mass? That is a question that we don't really understand just yet. Our third area is stellar feedback, and these are some beautiful images put together by Mihoko Yukita. The central one is what you would expect in 150 kiloseconds of Axis for M83, and for comparison, we have the Chandra image on the left. And the 2 things I want to bring to your attention is first, the diffuse emission, which is much clearer, much easier to see, and which we're detecting much better with the same amount of exposure with Axis. But also as we go to the edge of this field of view, again, as has been mentioned by a couple of people so far, the stability of the PSF and how now you can resolve these individual sources really well, and that can let you distinguish point sources from diffuse emission. And this will let us look at how the properties of the hot gas in H2 regions in star clusters depend on things like cluster mass or cluster age, and how that can give you conditions for breakouts and outflows, especially in comparison with multi-wavelength observations. We have 2 main questions in this area. How do star-forming structures arise from and interact with the interstellar medium? And what is the role of feedback from X-ray binaries, particularly as you go to high redshift? There is a really long particular question that I have failed at memorizing. If you would like me to tell it to you, I'm happy to look it up. But it's pretty cool, and it involves that role of X-ray binaries in reionization. I don't work at those redshifts, and I failed at memorizing that question. I'm sorry. But as you can see, there's lots of great science in there, but there's lots of room, which is why I've added these ... dots for many, many other questions that could be asked as part of GEO programs. We've started putting together our wish list of, this is what we would really like to do to address each of these questions. And so these are the early numbers that I've put here, but we're definitely still in the process of figuring everything that we want to do with this. Thank you.
So any comments or questions? So one thing I'm kind of interested in is the feedback links. I mean, so it's, you kind of get increased attendance sensitivity and you get the soft emission and then you can trace it with O3, but what do you think is kind of the most interesting case for feedback?
In the nearby universe?
Yeah.
I think, at least, I mean, this is my personal opinion, but I think pushing down to the lower mass scales and figuring out, okay, is it just that it all works the same in kind of like a self-similar sort of way, or when you get to smaller mass galaxies, some, maybe the energy escapes outwards and doesn't stay confined into an environment. I think we don't have enough systems where we've really mapped the hot gas of small galaxies. And I think that's where an area where access could be really interesting.
I am Will Zhang from NASA Goddard Space Flight Center. I will spend the next few minutes telling you about our plan to make an X-ray mirror assembly for access. First, let me acknowledge my technology development team. We call ourselves the Next Generation X-ray Optics team, consisting of, as of today, 14 people of scientists, engineers, and technicians alike. First, let me orient you a little bit about the access mirror assembly's characteristics in comparison to those of Chandra. Its focal length, outer diameter, PSF, and off-axis, on-axis PSF, effective areas at 1 keV and 6 keV, and the mass and total surface area. In comparison to Chandra, everything is much superior except the on-axis effective PSF. Okay. So this, in a way, this comparison shows the promise of access and the challenge of making this mirror assembly. So the threefold challenge of the access mirror assembly is as follows. Number one, it's good PSF. This requires fabrication, coding, and alignment of mirror segments to be very, very precise. And then in particular, also, we need to have very good on-orbit thermal environment, which is a good engineering challenge. Second aspect of the challenge is its large effective area. This requires precision, mass production, both in fabrication and assembly, and they must meet quality, schedule, and cost requirements. The third aspect is the lightweight. This requires the making of very, very thin and very lightweight optics, which is always challenging. And also, in particular, this requires us to understand and overcome distortions caused by gravity on the ground and by its release on orbit. Here is a block diagram, shows the mirror assembly, its overall structure. As the X-rays come from the sky, they first encounter the thermal pre-collimator, and then they pass it through the streetlight baffle and then get imaged, processed, reflected on the X-ray mirror to form images, and finally they exit the mirror assembly through the thermal post-collimator to reach the focal plane. Okay, the thermal and thermal collimators, both pre and post collimators, provide the thermal environment for the X-ray mirror to do its business. The streetlight baffles, of course, prevent streetlight from straight X-rays from reaching the focal plane. So this view graph shows the paradigm that we have for building the access X-ray mirror assembly. That consists of 3 major steps. The first step is to build mirror modules. The second step is to integrate these mirror modules into this intermediary step, which we call meta shells. And then finally, we integrate the meta shells into the mirror assembly. You can see this is a highly hierarchical process because this is what is needed for you to build a big and complex mirror assembly. So the technology aspect of this process is really in building this and qualifying this 150 or so mirror modules. And the integrating of these mirror modules into the metal shells and into the final mirror assembly is a well understood engineering process, although it does require development, but it's something that a lot of people know how to do. So what are the key technical elements of building a mirror module? First, we need to do mirror fabrication. We need to fabricate a lot of mirror segments. The basic process has been developed and understood, but we do need further development to improve its efficiency and to reduce its cost. The second technical element here is the coating. Okay, we use the standard atomic layer deposition. So this is a good process for minimizing the effects of thin film stress that can distort the mirror segments. Quite a bit more work is needed here to understand that the nucleation, the little balls of atoms formed by the atomic layer deposition process, we want to make sure that they do not scatter too badly to affect the point of spread function. The third aspect is the alignment. So this process is fairly standard and traditional. There's no not a whole lot of development needed. So we have understood this process, and the complication here is that this requires very, very good thermal control of the laboratory environment. So finally is the bonding process. And this I color coded in red because this is where we are spending most of our efforts to really understand the effects of epoxy shrinkage. So what's the process of building a mirror module? Okay, we start, of course, with the fabricating and coating a bunch of mirror segments. After the mirror segments have been coated and qualified, we use this back plate on which we're going to align and bond first pair of mirror segments, then the next pair, then the next pair. You can notice that this process has two features. One is that this is the highly repeated process, namely the first pair, second pair, third pair. Okay. The second feature, which is also very important, is that each pair of mirrors is independently aligned and bonded. As such, there is no stack-up error, even though the mirror segments are stacked on top of each other. So here is a diagram illustrating the mirror segment fabrication process. Just for your information, Access needs about 16,000, not 160, 16,000 mirror segments. We start the fabrication of a mirror segment with a single crystal silicon block measuring about 100 millimeters by 6 inches by 6 inches, or 150 millimeters by 150 millimeters. Then we use a standard machining process and lapping process to create a surface that is a good approximation to begin with of a mirror, X-ray mirror segment. Then we slice off this mirror shell, and the block goes back to be recycled for making the next segment, and this segment goes through a polishing and machining process to make the mirror segment that we need. In the end, this mirror segment is about 4 inches by 4 inches, or 100 millimeters by 100 millimeters, so smaller than the original block by about 1 inch on each of the 4 sides. So this mirror segment is good from the first millimeter to the last millimeter. Another thing to note is that on the back side of each mirror segment, we have these 4 little bumps, which will serve as alignment bumps and also serve as the hooks with which we are going to bond the mirror segments to the module. So what are the what's the status of the mirror segments fabrication? This view graph is meant to show that currently the mirror segments themselves are very, very good. As a matter of fact, they're better than Chandra's. Here is a comparison of the power spectral density of Chandra's mirror versus 2 of the mirrors that we have fabricated in the silicon mirror. You can see this, the black and the blue are substantially better than the pink, which represents Chandra. So the bottom line is that the apples comparison with the Chandra's mirror, these mirror segments are about 2 times better in figure quality and 30 times lighter and thinner and 30 times cheaper. So furthermore, we actually confirm the mirror quality as fabricated by X-ray measurements. So we were able to march down the X-ray image quality from about 5 arc seconds in 2017 to about 0.8 arc seconds in 2019. Okay, you can see this is a pair of mirror segments aligned and bonded and sitting in an X-ray beam for full illumination X-ray testing. So the technology status as of early 2022 is as follows. Early 2023, I'm sorry. A single pair modules built and tested. The image quality is about 0.83 arc seconds. And the building and test the multiple pair modules we hope to do, we are doing as we speak. We hope by early 2024, we will have something that is close to meeting access requirements. The plan for meeting access requirements is really build, test, learn, and iterate. So we'll continue to build and test the modules, more mirror segments, 2, 4, 6, and up to 24 mirror segments per module. And hopefully these modules will have better PSF starting at 2 arc seconds and to reach 1 arc second by later in 2023. We will test these modules both in terms of science performance and environmental, including vibration and the thermal vacuum. We may, depending on whether we have the wherewithal or not, start building a metal shell that will contain 3 co-aligned mirror modules. We will actually test this small metal shell. We hope that we will be able to reach TRL 5 for access by late 2023, reach TRL 6 for access by 2025. Okay, let me summarize. First of all, I want to point out that I would like to say that the single crystal silicon X-ray mirror technology has shown its potential to meet access's threefold requirements: good PSF, large effective area, and lightweight. But I want to quickly add that there is a lot more development that needs to be done to refine the mirror fabrication process, to improve its efficiency and to lower its cost, and to improve the atomic layer coating rate of iridium and to understand any effects of nucleation on PSF. And most important of all, we need to understand the behavior of epoxy to minimize its effects on mirror distortion. Or we need to devise a new method of bonding thin mirror segments to enable them to survive spaceflight launch environment. With that, I would like to thank you for your attention.
X-ray instrument, and this is the high-speed X-ray camera. I'm Eric Miller from MIT, and I'm the lead of the focal plane for Axis. These are the development teams. This is a collaboration among a number of universities, including my group at the MIT Kavli Institute and MIT Lincoln Laboratory, along with Stanford University. These 2 institutions are responsible for the detector development and development of the analog electronics. We're also working with Penn State in collaboration with the Southwest Research Institute, who are responsible for development of the digital electronics and the transient event monitor. And I do want to point out that all this work has been funded through over the last several years and continues to be funded by NASA through the APRA and SAT programs. So Chris showed this in the very first talk of this session. This is a table which shows the current requirements for the Axis instrument. And in fact, these requirements are such that Axis requires detectors with similar size, similar quantum efficiency, noise, and spectral performance to the CCD detectors that are currently flying on Chandrayaan and flew on Suzaku as well, with one very important exception, which is that they need to run significantly faster to avoid piling up photons on very bright point sources due to the very good spatial resolution and efficiency of the Axis mirrors. And in fact, they need to run 20 to 40 times faster than the Chandra and Suzaku CCDs. And I have this picture here because I want to point out this is a very simple instrument design. We have a single X-ray optic on the front of the observatory and a single instrument that does not move in any major way on the other end of the observatory. Okay, so the readout rate we need is about greater than 5 frames per second. And this is driving all of the technical advances that we're working on for AXIS. So this is the AXIS detector layout. This is a CAD drawing of it. The detectors that we've selected are MIT Lincoln Lab CCDs, and we're arranging them in four CCDs in a 2x2 layout like this. If you're familiar with Chandra ACIS I array, you should recognize this. It looks very similar to that. Each of these CCDs has 8 readouts, which is different from Chandra, and we have more pixels in the focal plane than Chandra ACIS I. We have about 8 megapixels total. The pixel size is the same as the ACIS CCDs, 24 microns, which will allow us to sample the 1 arcsecond PSF. We need to run at least 5 frames per second in order to get a pileup limit, which is less than Chandra's. Of course, we want to go faster than that, up to 20 frames per second, which is 16 to 70 times the Chandra ACIS readout rate. Another very important difference between the AXIS CCDs and those on Chandra Suzaku are that they're twice as thick, and this will allow us to have better response to hard X-rays up to 12 or even higher, even more keV. So we do have an AXIS detector prototype that we've been testing both at MIT and Stanford. This CCD has been developed by MIT Lincoln Lab, and there are really 2 key technical advances that allow us to run at these faster rates and still have the performance, the very good performance that we had on missions like Suzaku and Chandra. The first of these is an update into the design to the transfer gates that actually perform the bucket brigade parallel transfer of charge across the CCD. And this design allows us to do that transfer as fast as we need to for AXIS, but with very low voltage swings. And so, in fact, doing this transfer at the rates we need for AXIS, we use about the same amount of power that the ACIS CCDs use. So this is a very important technical advance that enable us to run these CCDs with low power. The other is at the point where the charge is read out from the CCD. This is another advance by Lincoln Lab to develop very low noise, very fast transistor amplifiers to enable that readout. And so using both of these advances on this CCD, which is called a CCID 89, we're able to demonstrate a lot of the performance that AXIS requires. So this picture on the right, this is an actual photograph of the CCD in our lab testbed circuit board that you can see. These CCDs are not exactly the same form factor that we need for AXIS. They're 2K by 1K pixel. However, they do have the same number of pixels that each one of the AXIS CCDs will have. They're 1.4 by 1.4 pixels. Has the same pixel size, the same number of output nodes as well. And so we're currently running these in the lab quite successfully at 2 megahertz pixel rate. So that's 2 million pixels per second that we read out. And to translate that to the equivalent AXIS CCDs, that's 7 frames per second. And so we're meeting our requirement for readout rate there. These are just 2 plots to show some of the performance that we're getting out of these CCDs. The plot on the left shows on the y-axis, this is the readout noise in electrons. So this is often quoted as a requirement because this affects the spectral resolution, especially at soft energies. On the x-axis, this is the CCD temperature. It actually, the very leftmost point there is minus 80 degrees. In fact, we will run even colder, so it's off the plot. But what this is supposed to show is that of the 8 segments that we have on these CCDs, there's 1 curve for each segment. 6 of them are achieving the readout, less than the required readout noise that we need for AXIS. And in fact, 4 of those are less than 3 electrons per RMS. And we expect that actually gets a little bit lower at lower temperature. So we're well on our way to meeting the requirements for readout noise so that we can get good soft response. The figure on the right shows the spectral resolution at about 6 keV. And so we're getting 135 eV full width half max at 6 keV, and this exceeds our requirement of 150 eV. And this is actually not the best segment. I'm only showing one here, but this is a representative segment of these CCDs. So we're currently doing low energy performance testing using a backside illuminated chip that we have in the lab. And I do want to say we'll have some updates at the head meeting in Hawaii on a couple of posters with results from that. Okay, so those are the CCDs. The front-end electronics are being developed both by MIT and Stanford. The real key advance here is, in fact, not something I would call front-end electronics, but it is what we call the MIT CCD readout chip, or MCRC. This is an external amplifier, meaning it's not actually on the CCD. It's not part of the readout node on the CCD, but it's located very close to the CCD. And in fact, it's this thing that's highlighted in orange here. This is the location where it will be on our test bed. When we actually design the flight package, it will also be very close to the CCD. This is a small 8-channel ASIC. And the whole point of this is that we're running so fast that we need to avoid essentially any backlog in the readout. And so we need to lower the capacitance of all stages of the readout as much as possible. And this ASIC that's been developed at Stanford allows us to do it. It has very low input capacitance. It also runs with very low power. By comparison, if we were to try to do this this output stage either on the CCD or using these 8 discrete amplifiers on this test bed, we would need 10 times the power. So this will enable us to run at the speed we need with the noise that we need and the low power that we need. Now, this has been tested at Stanford, and this little inset here shows results of that testing. You don't really need to understand what's being plotted here, except that this is the waveform from the output of a single pixel going through this ASIC. So this span here is 200 nanoseconds. This is running at an effective rate of 5 megahertz, which is faster than we need to run. And the key takeaway is that these waveforms have very sharp edges and they look very flat in the places they need to look flat. So this ASIC is operating exactly the way we need to. Now, we have not integrated with the CCD, but we will be doing that at MIT very soon, and expect some updates again on the operation of this at the head meeting in Hawaii. All right. So at the end of the analog electronics processing, we end up with a digitized signal. So we have basically a pixel stream running at 2 megapixels per second. So this is a total rate, and that's for each CCD. This is a total rate of 2 gigabits per second that is going into the digital electronics. There's no way we can telemeter all that information to the ground. And in fact, most of it is just empty sky. These are images of the sky. And most of those images do not have X-rays in them. And so we do what Chandra has done, what Suzaku does, what XMM does, which is to process those images and look for events that are X-ray candidates and only send down information about those X-ray events to the ground. However, once again, this has to happen very quickly. And so we need advances over previous generation of event recognition. And so this is work that Penn State has been doing now for several years to develop an FPGA-based event recognition processor, which does all of that event detection and characterization at the speeds that we need to reduce this 2 gigabit per second pixel input by a factor of 10,000 so that we have sufficient telemetry bandwidth to send that to the ground. In addition to providing that technology, Penn State is also providing the transient alert monitor. And so this will take that pixel stream, or that event stream rather, and compare that to onboard source catalogs and then detect in real time any sort of changes, either in flux or appearance or disappearance of events, of sources in the event stream. And so with using that, we can trigger an alert through TDRS to alert other observatories to transients. Now, this is based on development that Penn State has been doing for the past several years, which was initially to implement this on the Athena WFI as part of the science products module. Now, that hardware was not selected to fly on Athena, but this is really valuable for Axis, and all of the lessons learned and all of the development that went into that can now be used for Axis, for a key piece of the Axis instrument. Okay, so that's kind of a whirlwind tour. I'm certainly happy to talk offline about more of the technical details about this, but what I want you to take away is that the Axis X-ray camera really is a very simple design based on Chandra and Suzaku and other very successful instruments and missions, but it is running much faster, and that is a real hurdle to jump over. But the technology advances that we've accomplished are really going to allow this, and we're on schedule to demonstrate the technology we need by the proposal deadline, and also by the various design reviews that we have coming up. And so that's all I have, and I'm happy to take any questions.
Okay, so questions, and if you have any other general questions on the mirror or anything else, please feel free.
This is more of a general question, but early on, it was mentioned that the group response style with a very narrow orbit. Does it take into account any of the events on the other side of the Earth or anywhere?
That's a very good question. So there will always be the possibility of unfortunate findings. So, there can be transients in really bad parts of the sky or just in the sort of stuff, or something particularly bad for communications, and then maybe some fractional source of the the reality of it and the way that we phrase the requirements is that we'll have to be on a source, within 2 hours for some percentage of the transients. This is years, but with this minus, yes, and but it will be unfortunate. There may be some cycle sources for reasons of too much.
Okay, any other questions or comments? If not, I'll leave the last comment. Chris.
Don't forget the swag in the back. There's, if anybody wants some swag on the way up before Chris has the last comment, on those 2 chairs back there, feel free to take some stickers and some pins and tell your friends.
Yes, a lot of slides. I want to say something to thank Mike for the session together. Thank you very much, Mike. It's great to see so many people who have said voted at dinner time for this. If you're interested in active, please feel free to approach anybody, anyone acting in the leadership, to talk about it, share your ideas. Myself with Erin, who's the deputy PI, Richard, I will mention anyone else spoken here. Please feel free to come talk to us about active, and I look forward to seeing your observing proposal with 10 years now. Thank you very much, and thank you for saying so.